The quantum race, the global competition in quantum computing and its future applications. Alright, let's dive into one of the most intense high-stake technology races happening on the planet right now. The race to build a truly powerful quantum computer. And this isn't just about making faster gadgets. We're talking about something that could completely redefine everything from medicine to finance and even to national security. And things are really, really heating up. So, what's all the buzz about right now? Well, the whole thing kind of kicked into overdrive recently because of a massive claim from one of the heavyweights in this field, a claim that suggests we've just crossed a pretty monumental line in the sand. And there it is. That's the statement from Google that got everyone talking. I mean, just think about that for a second. They're basically saying their machine did something that is literally impossible for even the biggest, baddest supercomputers on Earth. This isn't just a small speed boost. This is what they call quantum advantage. But of course, that begs the huge question, right? Does this one achievement really mean we are in a whole new era of computing? Or is it maybe just one very impressive but single step on a much, much longer road? Let's dig in and find out. So this is definitely not just a Google show. This is a full-on global race with a bunch of major players, and each one has a totally different playbook for how to win. In fact, what's really interesting is that they don't even agree on what winning actually looks like. And this is just fascinating. Each of these companies is defining success in their own way. So you've got Google, and they are all in on this idea of quantum advantage, basically finding one specific gnarly problem that no normal computer could ever solve. Then you have IBM. They're playing the long game. Their goal is fault tolerance, which means building a machine that's super reliable and doesn't make errors. And then there's Quantium, focused on something called quantum volume. You can think of it like a combined score for quantum computers' overall power and quality. Their goal is just to be undisputed champ on that metric. Let's just zoom in on IBM's strategy for a minute. What's kind of cool is they've laid their entire roadmap out for the whole world to see. Each of these new chips with their awesome brand names is a very deliberate step forward their endgames. This fault tolerance system they're calling Starling. See, they're not really chasing quick headlines. They're trying to methodically build a foundation that's meant to last. And then you've got Continuum. This massive number you're looking at, 33.5 million. That's their latest quantum volume score. And remember, that's their measure of all-around performance. By putting out a number like that, they're making a pretty bold statement. They're saying, hey, our machine isn't just a one-trick pony. It's powerful, it's high quality, and it's ready for some seriously complex stuff. Okay, so we've talked about the race. Now let's get down to the engine that's actually powering all of this, the qubit. So the qubit or quantum bit is the absolute fundamental building block here. And the magic, the thing that makes it so different from the bits in your phone or laptop, is this wild ability to exist in multiple states at the exact same time. It's a property called superposition, and it's what makes all of this possible. This is the perfect way to think about it. A classical bit, the kind we've used for decades, is basically a light switch. It can be on or it can be off, 1 or 0, that's it. A qubit, though, is more like a coin spinning in the air. Before it lands, is it heads or tails? Well, it's kind of both, and their ability to hold all those possibilities at once is where quantum computers get their almost unbelievable processing power. But there is a catch. That spinning coin state is incredibly fragile. I mean, the slightest little thing, a tiny change in temperature, a stray bit of electrical noise, can make the whole thing just collapse. That's why these quantum computers look like giant futuristic chandeliers. They have to be kept in these super-controlled, ridiculously cold environments, and that is a massive engineering headache for every single team in this race. So how is this incredibly difficult, expensive race being paid for? Well, behind all the mind-bending physics and engineering, there's a huge wave of investment coming from all over. And everybody is betting that solving these massive challenges is going to have an even more massive payoff. Just take a look at this number for a second. $97 billion. That's the projection from magazine for what the quantum technology market could be worth by 2035. When you've got that kind of potential price on the horizon, it's no wonder so much money is flooding into the field. And this shows you it's not just some far-off dream. The money is pouring in right now. In 2024 alone, quantum startups pulled in around $2 billion. That's a 50% jump from just the year before. The belief in quantum's potential is absolutely translating into very serious cash. So where is it all coming from? Well, about two-thirds of it is private money, venture capital, corporate investment, and that sort of thing. But look at the other slice. A full third is coming from governments. That tells you that countries around the world are looking at quantum computing not just as a business opportunity, but as a critical strategic priority. Okay, so we've got a high-stakes race fueled by billions of dollars. But what happens at the finish line? What are the actual stakes here? Because a truly powerful quantum computer could be one of the most transformative and disruptive technologies we've ever created. So first, let's talk about the price, the upside. The potential applications here are just mind-blowing. Imagine being able to design brand new medicines by simulating molecules perfectly, something that takes years today, maybe in just days. We are designing revolutionary materials from the atom up, creating things that are stronger or lighter than we can even conceive of right now. This isn't just about small improvement. These are paradigm-shifting possibilities. But as always, with that incredible promise comes a pretty significant risk. A tool that powerful, a tool that can build new worlds, can also be a tool that breaks the one we already have. And that brings us to this concept cybersecurity experts call Q-Day. See, right now, basically all of our secure data, your online banking, private messages, military communications, all of it is protected by encryption that's based on math problems. They are simply too hard for any normal computer to solve. But a big powerful quantum computer could theoretically solve those problems in a snap, and Q-Day is the name for the moment that becomes a reality, the day our digital security as we know it breaks. Now, the good news is we are not just sitting around waiting for that to happen. Smart people have been working on this for a long time. In fact, this August, the US National Institute of Standards and Technology, or NIST, finalized a whole new set of encryption standards. It's called Post-Quantum Cryptography, or PQC. It's the start of a global upgrade to a new kind of security that's designed to be safe from both classical computers and quantum computers. So where does all of this leave us? Well, despite the incredible breakthroughs and the billions of dollars, the one thing everyone agrees on is that this is a marathon, not a sprint. We are seeing amazing progress for sure, but the real finish line is still a long way off. And why is that? Well, it comes down to this number, millions, because to do the really revolutionary stuff, the world-changing applications we talked about, experts agree we are probably going to need computers with millions of high-quality qubits. And wrangling millions of those super fragile things is a whole other level of difficulty. I think this quote from Professor Winfried Hensinger really puts it all into perspective perfectly. He's essentially saying that what Google did was a fantastic achievement, a huge scientific milestone. It proves these machines are getting more and more powerful, but it's just not the same thing as having the kind of universal fault-tolerant quantum computer that will truly change our world. So the marathon continues, but the pace is definitely picking up. We are out of the realm of pure theory now. We are firmly in an era of engineering, of competing strategies, and of real, tangible breakthroughs. The question is no longer if this technology will reshape our world, but when and what part of our world will it reshape first?